Hello everyone, this is 10.1, Sequences and Summation Notation. First, let's get into what a sequence is. A sequence is a function whose domain is the set of positive numbers. The terms of the sequence are represented as a list, a sub 1, comma a sub 2, comma a sub 3, up to a sub n. You notice there's an ellipse both before and after the a sub n. That is because sequences can either end at a sub n and be finite, or they can go on infinitely and not end. Let's start by looking at a very common sequence, the Fibonacci sequence. You can see here the list of the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21. They tell us that a sub 1 is 1, and they tell us that a sub 3 is 2. What they're telling us is that the first number in the list is 1, and that the third number in the list is 2. When they ask us for a sub 8, they're looking for the 8th term. So we have 1, 2, 3, 4, 5, 6, 7, 8. The 8th term is 21. The 9th term would be the next in the list. The way we find a term in the Fibonacci sequence is we add the previous two terms. So 13 plus 21 is 34. And the last term, the 10th term would be the sum of 21 and 34, which will be 55. Let's walk through another example together. Here on this example here, they want us to find the first four terms of the sequence whose nth term is given with a formula. Here they tell us that a sub n is represented by 2n plus 5. This means that a sub 1, the first term in the sequence, will be 2 times 1 plus 5, which is 7. A sub 2 will be 2 times 2 plus 5, which is 9. A sub 3 will be 11, and a sub 4 will be 13. This is a sequence that is linear. I'd like for you to go ahead and pause the video now and try to work out number 2 on your own. Try to find the first four terms in the sequence who's given by the formula a sub n equals negative 1 to the n over 2 to the n plus 1. Hopefully you've taken a shot at that, and here are the answers that I got. For a sub 1, the first term in the sequence, I got negative 1/3. The second term, positive 1/5. The third term, negative 1/9, and the fourth term, positive 1/17. You may notice that this negative here will cause our answers to flip back and forth, where odd numbered terms will be negative and even numbered terms will be positive, and the denominators increase at an increasing rate. Now let's go ahead and look at one example that's a little bit more complicated. So if you look at number 3 here, you notice that the format may looks a little different. We know a sub 1, the first term in the sequence, and we know the general formula for any other terms when n is greater than or equal to 2. So this formula tells me that the nth number in the sequence depends on the number before it. Okay, so if I have the first term, right, a sub 1, or the first term in the sequence is 3. If I want to find a sub 2, or the second term in the sequence, I take 2 times a sub n minus 1. That is 2 times the previous output we got from this sequence. So I'm going to plug in 3. This 3 here becomes our value, and I add 5 to it. I will get 2 times 6. 2 times 3 is 6, plus 5 is 11. The third term in our sequence will be 2 times the previous term, in this case 11 plus 5. So when we multiply this out, we get 22 plus 5, which is 27. And the fourth term in our sequence will be twice the third term plus 5. In this case, that will be 59. Just to recap, when we are using a formula like in this form, where I am plugging in a sub n minus 1, or the previous term in the sequence, when I know a sub 1, it becomes part of the second term in the sequence. That second term in the sequence, 11, becomes part of the sequence for the part of the third term in the sequence, and then the third term in the sequence becomes a component in the fourth term in the sequence. What's really going on here is that one term depends on the previous term. Now, what we call that more generally is right below us here. It is a recursive formula. A recursive formula defines the nth term in a sequence as a function of the previous term in the sequence. So the fifth term depends on the fourth. The third term depends on the second, and so on. We can do some of this work using our calculator. I am going to also post a video walking through the steps here, but the main things you want to know is if you hit second and then the stat button, you can move over to the list screen and select sequence. It should be an SEQ with an open parenthesis. That allows you to enter the expression, a variable, and the start and end points of a recursive of a sequence that will allow you to find any number of terms in a specific sequence. Like I said, I will post a video showing that calculator, kind of the buttons to hit, and you'll see that soon. We're going to move on to factorial notation. N factorial, which we write as n exclamation point, is the products of the numbers from 1 through the number n. So if we mathematically, n factorial is the same as n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. All the numbers, so if we wanted 5 factorial, it would be 1 times 2 times 3 times 4 times 5. Let's look at an example together. Here they want us to find the first 4 terms of the sequence defined by 20 divided by the sum of n plus 1 factorial. So when we find a sub 1, that is going to be 20 divided by, now our n value here is 1, so it's really 1 plus 1 factorial. 2 factorial is 1 times 2, so this is the same as 20 over 2, or 10. The second term in our sequence is 20 divided by 2 plus 1. 3 factorial will be 6, so this is the same as 20 over 6, which is the same as 10 over 3. Let's get a little bit more space for the next 2. A sub 3 will look like 20 over 3 plus 1 factorial. 4 factorial will be 4 times 3 factorial. So that'll end up being 24. So this is 20 over 24, which we can simplify to 5 over 6. And finally, the last term that we're looking for, our fourth term in the sequence, a sub 4, will be 20 divided by what ends up being 5 factorial, which is 24 times 5. So we end up with 20 over 120, which simplifies to 1/6. I'd like for you to turn over to the back of this worksheet and try examples 5 and 6 on your own. Take a second, pause the video now, and I'll work out these problems. You can check your answers in just a minute. Here in example 5, it looks like we may be dealing with some really large numbers, but that's not necessarily true. So looking at the numerator, I know that 14 factorial is 14 times 13 times 12 dot dot dot. Well, that's the same as 14 times 13 times 12 factorial. Why might I stop there? Well, I also have 12 factorial here in the denominator. So I can cancel the 12 factorials, and I'm left with 14 times 13 divided by 2, which I simplified to 7 times 13, which is 91. Over on example 6, I simplified the numerator. I know that n factorial is n times n minus 1 times n minus 2 dot dot dot, or n times n minus 1 factorial. I stop there because I have an n minus 1 factorial in the numerator and the denominator, which allows me to cancel in the numerator and denominator, and all I have left is n. All right, now we can move on to summation notation, our last definition of the day. Here's our definition. This is the sum of the first n terms of a sequence. And the way we write that, let me just zoom in here for us. We have the sigma notation where I equals 1 at the bottom and n is at the top. What this represents, it represents all the terms of the form a sub I from 1 to n. So we start at a sub 1, and we add to that a sub 2, a sub 3, all the way up to a sub n. Definitionally, I is what we call the index of summation, n is the upper limit of summation, and 1 is the lower limit of summation. I think the notation can look a little messy here, so let's look at one example together and make sense of really what's going on. So here we have our sigma, and it's telling us that we start at 1 and we end at 6, all terms of the form 2 times I squared. So we're going to end up with 6 terms. It's going to be 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared plus 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared. How did I know where to start? Well, this right here tells me that I need to start at 1. This 1 falls in right there. And this 6 tells me where to stop. The 1 is the lower limit of summation. 6 is the upper limit of summation. And we plugged each of the numbers from 1 to 6 in, and we're going to evaluate. Now we're going to end up with 2 times 1 here, 2 times 4 here, so that's going to be 8. 2 times 9 here will be 18. 2 times 16 is 32. 2 times 25 is 50. And 2 times 36 is 72. I'm going to add all these together using some grouping. This will be, 10 and 18 is going to be 28. Here I end up with, 82 plus 72. And I can see that 28 and 72 is 100. So fully evaluated, this summation will be 182. I'd like for you guys to try examples 8 and 9. Pause the video now. I'll walk through them in just a minute. But take a shot at them first, see if this is making sense. Over here on number 8, some things to pay attention to. We start at 3 and we end at 5. So I'm going to have 1, 2, 3 terms. My first term will be 2 to the third minus 3, which is 8 minus 3. That's where 5 is coming from. Here I have 2 to the fourth minus 3 in the middle. 2 to the fourth is 16. Minus 3 is 13. And for my final term, I get 2 to the fifth, which is 32. Minus 3 is 29. I add all those terms up, and I get 47. Let's go ahead and jump over to number 9. Be careful on this one. What we need to do is we need to find all the the sum of all the terms from 1 to 5 when I plug each of those integer values into 4. Well, there's nowhere to really plug it in, so I'm going to take 4 plus 4 plus 4 plus 4 plus 4. Really 4 times 5, and my final answer here will be 20. On numbers 10 and 11, you guys are going to go ahead and try these on your own first. Obviously, if you're unsure, you can just keep watching the video. But I want to just let you guys take a shot, see if you find the pattern, and we're going to try to express each sum in summation notation. Really, we're going to work backwards. Instead of creating a sum from a formula, I'm basically creating the formula. So pause the video now, try numbers 10 and 11, and in just 1 minute I will walk through how we can simplify these. Here's what I ended up with on number 10. Hopefully you see the pattern. What I noticed was this is 1 squared, 2 squared, 3 squared, up to 196, which is 14 squared. So that set up my upper and lower limits. I knew that I started with an I value of 1, and I ended with an I value of 14. And the formula we were using was we were squaring whatever that I value was. So if I were to plug in 1, that's where I get 1 squared is 1 right here. When I plug in 2, that's where this 4 comes from. 3 squared all the way up to 14 squared. Let's jump over to number 11. So let's talk again about the patterns we notice. What I notice here is that we start at 1 and then we end up dividing by larger and larger powers of 2. So that's where I started. I knew that we would have to be raising 2 to a negative exponent. But there's a couple things that make this a little bit more complicated. Well, I start with 1. My first term is 1, which means that if I want to turn 2 to some power into 1, I need to start at 0. So I need to start at 0 because when I plug in 0 as an exponent, I get 1 as a result. And then that would mean that this would be n, sorry about that. My first term in this sequence starts at 0, which is why I set my lower limit to 0. Now, the upper limit we also have to think about. Well, if I look at each of the denominators, what did I plug in to get 1/2? Well, this I value must have been 1. So if I wanted this to be 1, I must have started at 0. So the exponent that I'm raising it to will always be 1 less than the order in the sequence. So that's why, even though the exponent I have here is n minus 1, I know that that's the nth term in the sequence, explaining why I need an n as my upper limit of my summation. Our last task of the day, we're just going to talk about some properties of sums. So there's 3 properties, and they make a little bit of sense once you investigate a little bit. So if I look at the first sequence here, it's telling me that if I'm taking the sum of a product, of basically a scalar, I can take that scalar and move it out to the sum, in front of the sum, that is. So let's take an example. Let's say I had I equals 1, and I'm taking the sum. I goes from 1 to 4, and let's just use 3i squared. So if I were to write this out, the four terms of this sum, I would have 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared plus 3 times 4 squared. Well, what you might notice is that each of these terms, we have a GCF, right? We have a 3 here in each. So if I were to factor out a 3, I can write this as 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, this is just 3 times the sum from 1, I equals 1 to 4 of I squared times 3. That's our first property. Right? If I have a scalar multiplier, I can move it out in front because we would normally factor. What I'd like you to try to go ahead and do here is, it doesn't have to be a 2-column proof, but just try to show that these properties exist using a few examples. So I'll give you a starting point, and then we can pause our video and we can finish this up. I'd like you to try to prove each of these two properties using these two starting points. So for number 2, use the sum, let's go I equals 1 to 4 of I plus I squared. And see if you can show that property number 2 works, where the sum of a sum is really the sum of each sum individually. I know that sounded confusing. So that'll be your starting point for number 2. And your starting point for number 3 will be this summation. Let's use I equals 3, sigma symbol, 5 on top. And let's use I squared minus I cubed. So let's pause there. I'll work this out in just a minute, but I want you to go ahead and pause this and see if you can make sense of these two properties. So looking at our second property, I wrote this out. I wrote this as the sum of 1 and 1 squared, 2 and 2 squared, 3 and 3 squared, and 4 and 4 squared. What I did next is I used the associative property. I wrote this as the sum of 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 plus the sum of 1 squared plus 2 squared plus 3 squared plus 4 squared. The associative property allows me to regroup numbers and add in an order that I like better. And what we've shown, this in the left-hand parenthesis is the sum from 1 to 4 of all of the terms in the form I. And this over here on the right-hand side is the sum of all the terms of the form I squared from 1 to 4. One last problem, we'll look at that together. Alright, so I rewrote my difference summation here as 3 squared minus 3 cubed plus 4 squared minus 4 cubed plus 5 squared minus 5 cubed. Now, what I ended up doing there was summing all the positive terms together here in red, 3 squared plus 4 squared plus 5 squared, and then factored out a negative from each of the negative terms and created a summation inside the blue parentheses. What exists inside those parentheses is the summation of I squared from 3 to 5. And on the right, the summation of I cubed from 3 to 5, proving our 3 properties. Good work, everyone. Thank you. We'll stop there.